The simple sorts, bubble, selection, insertion, all share one flaw. Their running time grows like n squared, fine for a handful of numbers. But picture sorting a million of them. At n squared, that is about 10 to the 12th operations. A trillion. Even a fast machine crawls. There has to be a better way. And there is two algorithms that split the problem in half again and again and reach n log n. For a million, that is roughly 20 million operations, tens of thousands of times faster. Merge sort and quicksort. Let's see the trick that makes them fly. The whole idea has three moves. First, divide. Take the problem and cut it into smaller pieces, usually to halves. Second, conquer. Solve each smaller piece. And since each piece is the same kind of problem, you solve it the very same way, recursively, until the pieces are so tiny. The answer is obvious. Third, combine. Take those solved pieces and stitch them back into one answer for the whole. That final combine step is where the real cleverness lies. For sorting, the tiny pieces are trivial. An array with 0 or 1 element is already sorted. That is our base case. The only question is how we combine. Merge sort and quicksort answer it into beautifully different ways. Here is merge sort in 7 lines. If the array has one element or none, return it, it's already sorted. Otherwise, split it down the middle, sort the left half and the right half by calling merge sort on each, and then merge the two sorted halves. Watch what the splitting looks like. Start with the whole array. 5, 2, 8, 1, 9, 3, 7, 4. Merge sort doesn't sort it directly. It cuts it into a left half and a right half. Each half is still too big, so we split again, into quarters. And still again, until every piece holds a single number. Those singletons in green are the base case. One element is sorted by definition. The array has fanned out into a tree. Notice the shape. Every level cuts the sizes in half, so the tree is only about log n levels deep. Here, 3 splits to go from 8 down to 1. Splitting is easy. All the work happens on the way back up, when we merge. The merge step is the heart of merge sort. You are handed to halves that are already sorted, and you must fuse them into one sorted list. The trick is a zipper. Here are our two sorted halves. 1, 2, 5, 8 on the left, 3, 4, 7, 9 on the right. Below, an empty output. We keep a finger on the front of each half. The rule is simple. Compare the two fronts, take the smaller one, drop it into the output, and advance that finger. Repeat. Because both halves are sorted, the smallest thing left is always one of the two fronts. 1 versus 3. 1 is smaller, so 1 goes down first. Now 2 versus 3. 2 wins. 5 versus 3. This time the right side is smaller. 3 drops in. 5 versus 4. 4 is smaller. Take it. 5 versus 7. 5 goes. 8 versus 7. 7 is smaller. 8 versus 9. 8 goes down. Now the left half is empty. When one side runs out, there is nothing left to compare against, so we simply copy whatever remains on the other side, already in order. Just the 9. And the merge is complete. 1, 2, 3, 4, 5, 7, 8, 9. Perfectly sorted. And here is the beautiful part. To merge two lists of total length n, we touched each element exactly once. So a merge costs order n. Linear. So let's run the whole merge up on our array. Start at the bottom of the tree. 8 sorted singletons. Merge them in pairs. 5 and 2 become 2, 5. 1 and 8 stay 1, 8. 3 and 9. 4 and 7. Each pair now sorted. Merge the pairs into 4s. 2 5 zippers with 1 8 to give 1, 2, 5, 8. 3 9 with 4 7 gives 3, 4, 7, 9. And one last merge. The very zipper we just traced fuses the two 4s into the whole sorted array. 1, 2, 3, 4, 5, 7, 8, 9. That is merge sort, top to bottom and back up. Why does this give n log n? Look at the work laid out by level. The top level is one problem of size n. The next level is two problems of size n over 2. The one below, 4 of size n over 4. But here's the key. At every single level, the pieces still add up to n. Each level does order n work in total. And how many levels are there? Since the size halves each time, you can only halve n about log n times before you hit 1. So it's n work per level times log n levels. Multiply them. N per level times log n levels gives n log n. And this is why merge sort is so dependable. Best, average, or worst case, it is always n log n. It never has a bad day. Quicksort takes a different route. No merge step at all. It picks one element as a pivot, then partitions the array so everything smaller sits to the pivot's left and everything larger to its right. The pivot lands exactly where it belongs. Then it recurses on each side. Here we pick the pivot as the last element and keep a store index marking the boundary of the smaller than pivot region. Let's partition a small array and watch the pivot settle. Our array 3, 7, 2, 6, 4. The pivot is the last element, 4, marked in rows. The store index starts at the far left, position 0. Now scan from the left with the second finger, comparing each element to the pivot 4. Position 0, 3. Is 3 less than 4? Yes. So it belongs in the small region. Swap it with the store slot, which is itself, and push the store index forward to 1. Position 1. 7. 7 less than 4? No. Leave it where it is, and the store index does not move. Position 2. 2. 2 less than 4? Yes. Now the swap actually moves things too. Trades places with the 7 sitting at the store index. The array becomes 3, 2, 7, 6, 4, and the store advances to 2. Position 3. 6, 6 less than 4? No. Skip it. And that's the end of the scan. The final move is the payoff. Swap the pivot into the store slot. The 4 trades with the 7 at index 2. And now look. 3, 2, 4, 6, 7. The pivot 4 is now in its final, permanent position. Everything to its left is smaller, 3 and 2. Everything to its right is larger, 6 and 7. 4 will never move again. Now quicksort simply repeats itself on the two sides. Sort 3, 2. One more partition flips it to 2, 3. The right side, 6, 7, is already in order. Glue the pieces around the pivot, and the whole array comes out sorted. 2, 3, 4, 6, 7. Every pivot, as it settled, dropped one element into its final home. No separate merge needed. That is quicksort. But quicksort has an Achilles heel. Its speed depends entirely on the pivot. Pick pivots that split the array evenly, and you get log n levels, n log n on average. But feed it already sorted data while always picking the last element, and every partition peels off just one element. The tree becomes n levels deep, and it collapses to n squared. The cure is to pick the pivot randomly, or as the median of 3. Your turn. Here are two already sorted halves, 2, 5, 8, and 1, 3, 9. Pause the video and merge them by hand using the zipper. Compare the fronts, take the smaller, repeat. What sorted list do you get? I'll wait. 2 versus 1. 1 is smaller. It goes first. 2 versus 3. Who wins? 5 versus 3. 3 is smaller. 5 versus 9. 5 goes. 8 versus 9. 8 goes. Left is empty now. So we copy the last of the right, the 9. And the answer is 1, 2, 3, 5, 8, 9. If you got that, You have the merge step cold. Trap 1. The big one. Quicksort is not always fast. A bad pivot, like always taking the last element of already sorted data, drives it to n squared. Randomize the pivot, or take the median of 3, and this almost never happens. Trap 2. Merge sort is not in place. That tidy merge needs a separate output array, so it costs order n extra memory. Quicksort, by contrast, partitions inside the array itself. Trap 3. The zipper merge only works because both halves are already sorted. Take the fronts of two unsorted lists and you get nonsense. Sorting the halves first is what earns you the linear merge. And trap 4. Recursion depth. Balanced, the tree is log n deep. Badly unbalanced, it stretches to n. Either way, remember each level of the tree does order n work in total. That's the product that sets the running time. Let's put it all together in one table. On the left, the basic sorts, bubble, selection, insertion, all stuck at n squared. Merge sort is always n log n. It is stable. Equal elements keep their order, but it pays order n in extra space. Quicksort is usually n log n and works in place. But it can degrade to n squared on a bad pivot, and it isn't stable. But both share the one big idea worth remembering. Divide the problem in half, conquer each half recursively, and combine. And n squared collapses to n log n. Merge does its work combining. Quicksort does its work dividing. Master that trade, and you understand fast sorting. That's divide and conquer.